Evaluate the following definite integral. So we have the integral from 0 to 1 of 1 by the square root of 2t minus t squared I hat plus t times the natural exponential raised to the 4t j hat. So looking at this given vector value function here, I think it's going to be easiest to start by integrating these components separately. So we've got a lot going on with this problem. So we want to integrate each component separately, and then we'll put our final answer together at the end. So starting off here with the f component, so that's the integral from a to b of f of t dt. And here this is defined as the integral from 0 to 1 of 1 divided by the square root of 2t minus t squared dt. So looking at this integrand here, it's not set up as given for a u substitution, but we can manipulate the radicand here to allow ourselves to use a u substitution. So in order to do that, what I want to do is complete the square for the radicand. So complete this square, and then you can either use a u substitution or a trig substitution. So thinking about what we're given, we have minus t squared plus 2t. And I'm just going to pull that negative out, because when we're completing the square, you don't want your leading coefficient to be anything but 1. So I have minus parentheses t squared minus 2t. So we can now identify what is the coefficient of the variable of degree 1, which is minus 2. So we'll use this to complete the square. So I have minus t squared minus 2t. And to complete the square, we take that coefficient, negative 2, divide it by 2, and square it. Now be careful. We can't just add this constant here. We want to technically do nothing, so we need to subtract the same thing. So that's minus negative 2 divided by 2 squared. So what is this leaving us with? Well, we now have minus t squared minus 2t. Negative 2 divided by 2 is minus 1. So negative 1 squared in both cases leaves us with 1. So we'll have a plus 1 minus 1. So we can see here these first three terms, there's the square of your binomial. So we can rewrite this as minus, so this becomes t minus 1 squared minus 1. And there's nothing wrong with this. We can leave it as it is, or we can take this negative from the outside and distribute it back through. I leave that up to you. So I'm going to distribute mine and rewrite this as 1 minus t minus 1 squared. So this is equivalent to our original radicand, and let's just rewrite that definite integral. So we have manipulated this so that we're left with the integral from 0 to 1 of 1 divided by the square root of 1 minus t minus 1 squared dt. And so this is much nicer. We can easily use either a trig substitution or a u substitution. You can pick your favorite method and go from there. So I'm going to use a u substitution at this point. I'm going to go ahead and let my u be t minus 1. So differentiating with respect to t, we have du dt is just 1, or just du is equal to dt, and that is a minus in between. Now, we have to be careful here because we're using a definite integral. So we're going to need to change our bounds. And the reason for changing our bounds is that the bounds 0 to 1 belong to t. T is an element of the closed interval from 0 to 1, but we're changing our variable to u. So we can think about our u substitution here as a function of t. U of t is equal to t minus 1. So let's change these bounds. We have u of 0, is going to be equal to 0 minus 1, which leaves us with negative 1. And then we have the function u of t evaluated at 1 leaves us with 1 minus 1, which is 0. And so these are the new bounds for u that we're going to plug in with our u substitution. The bounds on the new variable u are from negative 1 to 0. So let's plug these in and see what we're left with. So we have the definite integral. So 0 we know becomes negative 1, and 1 becomes 0. And now plugging those substitutions in, we have 1 by the square root of 1 minus u squared du. And hey, this is a general antiderivative. Woohoo! This integrates to inverse sine or arc sine of u. And we're ready to go right ahead and evaluate from negative 1 to 0. So let's see, we have arc sine of 0 minus arc sine of negative 1. And we know that sine of 0, of course, goes to 0, or inverse sine of 0 goes to 0. And inverse sine of negative 1 goes to minus pi by 2. So we have negative times a negative, leaving us with a beautiful final answer of pi over 2. So this is the definite integral for the f component of our vector. And now we need to go ahead and evaluate the g component. So we have the definite integral from a to b of that g component, g of t dt. So this is the integral from 0 to 1 of t times the natural exponential raised to the 4t dt. And so in this case, we're going to need to go ahead and use integration by parts. So let's just quickly recall our integration by parts. That is the integral of u times dv, and this breaks down to u times v minus the integral of v du. So we need to go ahead now and define what's u and what's dv. So fortunately, recall that we have an acronym for that, for choosing our u. And the acronym is ILATE. So what do these letters in our acronym mean? Is there an inverse trig function? Is there a logarithm? Is there an algebraic expression? Is there a trig function? Or is there an exponential? And we go in order of the acronym, looking at our integrand to determine your u. So here we go. Looking at this integrand, do you see an inverse trig function? Nope. Do you see a logarithm? Nope. Do you see an algebraic expression? Sure do. It's t. So that's what our u is going to be. So we can say, for our integration by parts, that u will be the algebraic expression t. And whatever is left over is your dv. So our dv here is the natural exponential raised to the 4t dt. So from u, we need to differentiate to attain du, which in this case is just dt. And now from dv, we need to integrate to attain v, which will be the natural exponential raised to the 4t by 4. So these are the integration by parts substitutions that we're going to need in order to evaluate this. So we'll give ourselves plenty of room. So here we go. This will become, again, that's u times v minus the integral of v du. And plugging in what we have t times the natural exponential raised to the 4t divided by 4, and we are evaluating this from 0 to 1 minus the integral from 0 to 1 of v du. So that is the natural exponential raised to the 4t by 4 dt. And we're excited because we see that this new definite integral is a general antiderivative. So I'm going to hold off on evaluating until the very end. So we can rewrite this as t times the natural exponential raised to the 4t by 4. And this will become minus the natural exponential raised to the 4t divided by 4 times 4, which is 16. And now we can evaluate the whole expression from 0 to 1. So here we go. Plugging in 1, we'll end up with the natural exponential raised to the 4 by 4 minus the natural exponential raised to the 4 by 16 minus, now we are evaluating the antiderivative at 0. So the first term just goes to 0 minus the natural exponential raised to the 0 divided by 16. And look at all this nice simplification here. With these first two terms, we can actually get a common denominator if we multiply by 4. And we know, of course, that the natural exponential raised to the 0 goes to 1. So the only thing, of course, to be mindful of is the negative. So this is going to leave us with, we have 4 times the natural exponential raised to the 4 minus the natural exponential raised to the 4 over 16. Negative times a negative gives you plus 1 over 16 with a common denominator and everything. So our beautiful final answer for this term is going to be 3 times the natural exponential raised to the 4th plus 1 divided by 16. Whew! That's a great example. Lots of review there. But we're not done. We've got to plug this back in. So giving ourselves plenty of room. All right, so at the beginning, we were given the definite integral from 0 to 1 of 1 divided by the square root of 2t minus t squared I hat plus t times the natural exponential raised to the 4t j hat dt. And we just integrated to find that our beautiful final answer here is going to be pi over 2 I hat plus 3 times the natural exponential raised to the 4 plus 1, and that's all divided by 16 multiplied by j hat. And this is our beautiful final answer for the evaluation of our definite integral of the vector valued function.